Good evening and welcome back. Tonight's lesson is going to be focusing on stoichiometry, or more specifically reaction stoichiometry. You had an introduction to composition stoichiometry in first semester, which is basically dealing with the mole concept when we're talking about a single substance. The reaction stoichiometry is going to be looking at the relationship in terms of moles between reactants and products in a chemical reaction. You'll use mathematical and computational thinking to identify and solve different types of reaction stoichiometry problems, and you will look at the concept of limiting reactants and percent yields during this unit. Stoichiometry is the analysis of the quantities of reactants and products in a chemical reaction. Those calculations will depend upon the relationship between the number of moles of each reactant and product. Once we have that molar relationship, which we can use by looking at the correctly balanced equation, we can then convert to any of the other quantities that we have learned previously, whether that is dealing with mass by using the molar mass, volume of a gas at standard temperature and pressure, STP, using the 22.4 liters, or using Avogadro's number 6.02 times 10 to the 23rd power to convert from the moles into atoms or molecules, ions, particles, whatever it happens to be. We can look at the reactions in terms of just the molecules that we would see. Again, you can look at the coefficients for the balanced equation to give you the relative number of molecules. You could look at it in terms of the amount of moles, which we can say is just going to be the relative number of molecules or coefficients that we have from the chemical reaction, and I'll go through and show you an example of that in just a few minutes. We can look at it in terms of the atomic mass units, and just basically looking at molar masses. We can look at the mass itself. Now this one here, the mass and the total mass, that is going to represent the law of conservation of mass, which hopefully you remember. Just simply states that mass cannot be created or destroyed. It is simply changing forms. So essentially whatever the total mass is for my reactants, that should be the total mass that I would get for my products at the end of the reaction. We're going to begin by looking at the mole ratio, which tells us the number of atoms or molecules in each reactant or product shown as the ratio of the moles. When we look at this, this is what we will use to convert from one substance to another within the chemical reaction. So we have a couple of example problems here. The first one, I'm going to show you guys how we actually determine what that mole ratio is if we were going to do all the stoichiometry, and then the second one we'll look at just the shortcut for how these things relate to each other. So if we look at the first problem, recognize that a chemical equation represents how molecules react. So I have 3 hydrogen molecules reacting with 1 nitrogen molecule, and it produces 2 ammonia molecules, NH3. So in order to determine the mole ratio, we would need to convert from the molecules into the number of moles. So I'm going to start by doing that. So I'm going to take 3 molecules of H2. Remember, I can abbreviate molecules as MC. That is a me thing, not a universal. So if you're looking at this from somewhere other than my class, make sure your teacher knows that you're talking about molecules here. So I'd have 3 molecules of H2, and I know that for every 1 mole of H2, I would have 6.02 times 10 to the 23rd molecules of H2. And if we do that, that gives us approximately 5 times 10 to the negative 24th for my number of moles of H2. If we do the same thing, we have 1 molecule of N2, and we know that for every 1 mole of N2, there are 6.02 times 10 to the 23rd molecules of N2, and that would give us approximately 1.67 times 10 to the negative 24th moles of N2. And then finally, I have 2 molecules of NH3, and we know that 1 mole of NH3 will be the equivalent of 6.02 times 10 to the 23rd molecules of NH3. And if we do the division on this, we end up with approximately 3.33 times 10 to the negative 24th moles. So if you remember when we were looking at empirical formulas, and you would take the smallest number of moles and divide all of them by that number to get the ratio, if we did the same thing and we took all of them and divided it by 1.67 times 10 to the negative 24th, they're all moles, I would end up with a 3:1:2 ratio. And if you notice, those numbers correspond exactly with the coefficients from our balanced chemical equation. So because of the fact that we're dividing each of the number of molecules by the exact same number, Avogadro's number, 6.02 or 6.022, depending on your teacher, you have all of these numbers being divided by that same value, so the ratio will be identical to what the original number of molecules happens to be. So what this means for us is that when we are setting up our conversion factors, and here's where I'm going to go over to example number 2. If I want to set up conversion factors for the calcium nitrate compared to everything else, I would simply have, again, 2 moles of the Na3N over the 3 moles of CaNO3 parentheses 2. I could have 1 mole of Ca3N2 over 3 moles of CaNO3 parentheses 2. And I could also have 6 moles of NaNO3 over 3 moles of CaNO3 parentheses 2. So this will allow us to convert from any given amount of one substance in a chemical reaction into the products or another unknown substance, if it is a reactant, for another part of that chemical equation. All right, so you have just a few simple steps that you need to do to solve any stoichiometry problem. The first one is to balance the chemical equation. Again, that will allow us to have that mole ratio set up. Once we have that, you want to convert whatever your given quantity is into moles, and then convert from moles of the known or the given substance to moles of the unknown substance. And then finally, whatever the problem's asking you to solve for, if it's something other than moles, you would convert from moles of that unknown into whatever the desired unit happens to be. So you may remember previously we had a mole roadmap that we used back in the fall. We're going to expand that roadmap out. Hopefully you'll notice here, if we just drew a line straight down the center, we would have the exact same roadmap that we did in the fall. So we can fill in a couple of pieces of information here. So again, if we're trying to go between mass and moles, this would be represented by the molar mass, again, the number of grams found in 1 mole of a substance. We would have the volume of a gas at STP, which would be the 22.4 liters. And then we have your atoms, Avogadro's number, 6.02 times 10 to the 23rd. For your number of atoms or molecules, ions. So I'm going to fill that in over here on the other side as well. So we have molar mass, we have 22.4 liters, and we have 6.02 times 10 to the 23rd for your atoms or molecules. So that leaves us with one last thing, and this line here between the moles of the given and moles of the unknown, that would again represent the molar ratio that we just got done discussing. And again, the molar ratio will be your coefficients from your balanced chemical equation. And if you don't remember, I abbreviate BCE as balanced chemical equation. So when we're looking at any of these things here, just remember, all these are doing is setting up a conversion factor for us, 2 things that are equivalent, just with different units. So I'm just going to focus on the volume of the gas concept here. So again, just as an example, depending on what we're starting with, where we're trying to go, I could either have 22.4 liters over 1 mole, or I could have 1 mole over 22.4 liters. Whichever one causes the unit that is given to cancel out, that's one that we're going to use. Okay, so let's look at a few example problems here to help illustrate this stoichiometry concept. So we're going to begin by looking at the combustion of propane. It says that propane, C3H8, is a fuel used in many gas grills. It combusts according to the following equation. So when we look at this reaction again, we need to have it balanced. So not going to waste your time going through all the balancing process here, but I would have 1, 5, 3, and 4 for the coefficients. And now the first part there says use unit factors to determine how many moles of oxygen are needed to completely react with 2.5 moles of propane. So in this case, the 2.5 moles, that is my given information. Propane is my initial substance. I'm trying to solve for moles of O2. So I'm going to begin by taking the 2.50 moles of propane, C3H8. A little better. There we go. And in order to convert from the moles of the propane into moles of oxygen, I need to use my molar ratio. So looking at my coefficients, I have moles of propane in the numerator, so I'm going to place the moles of propane in the denominator to get them to cancel. So I have my moles of C3H8, and I would have moles of O2 in the numerator. My coefficient for oxygen is a 5. My coefficient for propane is a 1. So that will cancel my moles of propane. I'm left with moles of oxygen. So I just need to multiply this out, and I would end up with 12.5 for my moles of O2. Please remember significant figures. 2.50, that has 3 significant figures. So 12.5 would be rounded to 3 significant figures. Okay, so if we move on to the next one, now notice it says how many molecules of CO2 form when 3.5 moles of oxygen react. So in this case, again, I'm starting with moles, but now I'm solving for molecules. So I don't have to do any conversion on the front end to get to my mole ratio because I'm starting with moles, but I am solving for molecules. So I'm going to have a 2-step process for this problem. So if you want to pause it for a second, go back and look at your roadmap on the previous slide. You can see the conversions that you would need to set this problem up. So I'm going to begin with the 3.50 moles of oxygen. And from my chemical equation, I know that for every 5 moles of oxygen, there are 3 moles of CO2 that are produced. And my conversion from moles to molecules, 1 mole of CO2 would be 6.02 times 10 to the 23rd molecules of CO2. My moles of CO2 would cancel, my moles of O2 would cancel, and I'm ready to solve. And when we plug our numbers in, we end up with 1.26 times 10 to the 24th molecules of CO2. All right, for our next problem, how many grams of steam form when 4.50 times 10 to the 22nd molecules of CO2 form? So in this instance, this is the first example where we're not starting off with moles, so we need to first convert our given substance into moles. So I'm going to begin by taking the 4.50 times 10 to the 22nd molecules of CO2, and we're going to convert that into moles. So 1 mole of CO2, 6.02 times 10 to the 23rd molecules. That now gets me into moles. So now I can go to my mole ratio. Again, pause the video and go back to the roadmap if you need to. So I have 3 moles of CO2 in the denominator, 4 moles of steam or water vapor in the numerator. And now I need to go to grams. So if you remember calculating the molar mass, if you look at your periodic table, hydrogen has a mass of 1 approximately. Oxygen has 16, so 2 atoms of hydrogen plus the 1 atom of oxygen gives me a total of 18, and it was 0.02 grams of water in 1 mole of water. And now we're ready to solve for this one as well. So you should hopefully get 1.80 for your grams of water. All right, and now we have one last example problem here. How many moles of C3H8 must react to produce 250 liters of CO2? So in this case, we're starting with the product, and that is not a big deal. So don't think that you always have to start with a reactant, because you don't. It can be anything within that chemical reaction. So I'm going to take 250. Notice here I have only 2 significant figures because there's no decimal point showing. So I have 250 liters of CO2. For every 1 mole of CO2, what's that? I have 22.4 liters of CO2. And now I can do my mole ratio. Notice I'm solving for moles, so once I get that mole ratio, I am done. So for every 3 moles of CO2, 1 mole of propane was used. And now we can solve, and we should end up with approximately 3.7 moles of propane. So the next problem we're going to look at is dealing with the active ingredient in Tums antacid is calcium carbonate, which can neutralize stomach acid, which is essentially hydrochloric acid, as shown in the following equation. So we have CaCO3 plus HCl yields H2O plus CO2 plus CaCl2. So going for our balanced equation for this, I would have a 1 for the calcium carbonate, I would have a 2 for the hydrochloric acid, and then I should have a 1, 1, and 1 for the water, carbon dioxide, and calcium chloride. So the first question says calculate the mass of the calcium carbonate that is needed to neutralize with 65 grams of stomach acid. So we have a mass to mass problem. So we're going to start with the grams of the HCl, and we're going to convert it into grams of the calcium carbonate. Again, we cannot go directly between the grams and the grams. We have to go through the moles. So I'm going to begin by taking 65.0 grams of the HCl. Using your periodic table, 1 mole of the HCl, 36.46 grams. And from there, we now can get out of moles of the HCl and into moles of the calcium carbonate by using the molar ratio. So I have a 2 for the coefficient for the HCl. So I have 2 moles of HCl, and I have 1 mole of the calcium carbonate. And now finally, we need to convert to mass of the calcium carbonate. So using your periodic table once more, you have 1 mole of the calcium carbonate in the denominator, and we should have 100.08 or 09 for my grams of calcium carbonate. So if we plug all of those numbers in, we should end up with approximately 89, and it's 0.22, but with 65.0 we have 3 significant figures, so we just round that to 89.2 grams of calcium carbonate. So just a quick little reminder here, when you are doing your problems for your test, just remember I want to see both the unit, grams, moles, liters, whatever it happens to be, and the substance. This is going to really help you stay organized through your work and make sure that you don't accidentally invert your numbers improperly. So always have your unit and the substance, and that will help you with the canceling. You'll notice here again, grams in the numerator, grams in the denominator for the HCl, moles of HCl, numerator, denominator, moles of the calcium carbonate, and then I'm left with my grams of calcium carbonate in the numerator for the last conversion factor. All right, so let's now look at our next one. We have the volume of carbon dioxide that's being produced when 125.0 grams of the stomach acid is reacted completely, assuming STP. So again, we have a mass to volume type of problem here. And if we set this up, we are going to start again 125.0 grams of the HCl and 1 mole of the HCl, 36.46 grams. We now look at our molar ratio. Again, I have 2 for the HCl and I have 1 for the carbon dioxide. So I'd have 2 moles HCl, 1 mole of the CO2, and then from there, trying to get into volume, assuming STP, so I'd have 1 mole of CO2, and I would have 22.4 liters of CO2. And now I'm ready to solve. So when I plug all those numbers in, we need, in this case, with 125.0, that's going to be 4 significant figures. So I would have 38.40 liters of CO2. Grams of HCl cancel, moles HCl cancel, moles CO2 cancel, and I'm left with liters of CO2. All right, last problem. Calculate the number of molecules of hydrochloric acid that must have reacted to produce 40 grams of calcium chloride. So in this case, again, I'm starting with 40 grams, 40.0. That's going to be 3 significant figures, and I'm going from the CaCl2 back to the HCl. So if we start off with that, 40.0 grams calcium chloride. We're starting with grams, so I need to use the molar mass. So I have 2 times 35.45 for chlorine plus 40.08. So that should be, I believe, 110.98 grams of the calcium chloride. And now, to get rid of my moles of calcium chloride, I'm going to put 1 mole of calcium chloride, again, because its coefficient is 1, and 2 moles of HCl, because its coefficient is a 2. And then finally, because I'm going to molecules, I will say 1 mole of the HCl is equivalent to 6.02 times 10 to the 23rd molecules of HCl. And now we're ready to solve. So 40 divided by 110.98 times 2 times 6.02 times 10 to the 23rd. And that should give us 4.33, or sorry, 4.34 by rounding up, times 10 to the 23rd molecules of HCl. So we're now going to begin the second portion of this lesson, which is dealing with reactions that occur in non-perfect stoichiometric amounts. So what does that mean? Well, if we look at the diagram below, we have a reaction that's taking place where we have H2 molecules reacting with O2 molecules, and they're producing water. So if you think about your balanced equation, we would have H2 plus O2 forming H2O, and if we were going to balance it, we'd have 2 for the coefficient of H2, and we'd have 2 for the coefficient of water. So now here's where I really want you to dive into what's taking place inside of each of these different reaction vessels. So before they're mixed, if you look at the total numbers, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 molecules of the H2. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 molecules of the O2. So hopefully you could notice with that, because I have the same number of molecules, that would mean that I have the same number of moles. However, when you look at your balanced equation, I know that for every one molecule or every 1 mole of O2, I have to have 2 molecules or 2 moles of the H2 that reacts with it. So at some point in this reaction, we're going to have one of those 2 reactants run out. And this is a concept that we're going to talk about, which is called a limiting reactant. So when I look at my product vessel, you'll notice that I have now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules of water that are produced, but I also have some of the oxygen molecules that are left over. So if we count those, 1, 2, 3, 4, 5, we have 5 molecules of O2 that are left unreacted. The reason why they're unreacted, there's no more hydrogen gas to use. So that's why you don't see any hydrogens in here, because they were all consumed during the production of the water. We're now going to begin to focus on the application of stoichiometry, and the first thing that we're going to look at is a limiting reactant. So what is our limiting reactant? This is simply going to be the substance in the chemical reaction, has to be a reactant that determines how much of the product can be made. It is whatever produces the fewest moles of a product. It doesn't matter which product you go to, depending on the way how the question is worded. Sometimes it's just asking you for a limiting reactant, and you get to choose. Other times they'll tell you to solve for a certain amount of a product, and then you'd go to that product. But whichever one is producing the fewest number of moles of that product, that will be your limiting reactant. The excess reactant is going to be the reactant that will not run out, so it would produce the larger amount of the product, or you'd have the molecules of that substance left over, as you saw in the previous example. So let's now look at a couple of example problems here to help you kind of figure out this concept. So we're going to use the reaction between nitrogen and hydrogen gas to form ammonia. And as you saw previously, we have N2 plus 3H2 forms 2NH3. So in this first diagram that we see here, we are looking at a perfect stoichiometric mixture for these. So what that means to me is that I have exactly the right number of moles of both reactants to produce the maximum amount of product. So we would have nothing left over. So in an ideal world, this is what we would want. However, you can see here in the picture, I have 1 molecule of N2 and I have 3 molecules of H2 for each of the little circled sets of molecules, and those will each produce 2 molecules of NH3. So I have nothing left over. There is no limiting reactant. There is no excess reactant. As we now turn our focus to a non-perfect stoichiometric mixture, or a limiting reactant mixture, using the same example, I have in this case now 1, 2, 3, 4, 5 molecules of N2. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules of H2. So in this case, because my ratio is 1 to 3, I'm only going to use 3 molecules of N2 to go along with the 9 molecules of the H2. So that means that I have 2 that are left over. So these 2 would be the excess reactant, in this case the N2, because the hydrogen is going to get completely consumed and I'll have none left. So when I look after the reaction, I'd have the 6 molecules of the NH3 that would form from the reaction. Again, 6 atoms of nitrogen in those 3 molecules. I have 18 atoms of hydrogen in those 9 H2 molecules. So I have 6 molecules of NH3 that get produced, and then I have the 2 nitrogen molecules that are left over as the excess reactant. Now going to look at an analogy to help us with this limiting reactant concept. So when we look at the creation of a sundae, we would need 12 ounces of ice cream, which would be approximately 2 scoops. We would need 1 cherry, and we would need 50 milliliters of syrup in order to make 1 sundae. So if we were given these ingredients, where we had 8 scoops of ice cream, we had 3 cherries, and we had 100 milliliters of syrup, you should be able to determine how many sundaes you would make using each of those individual ingredients. So since I only need 2 scoops of ice cream, but I have 8, I could, in theory, if I were to use up all of the ice cream, I could make 4 sundaes using the ice cream. Looking at my cherries, and I only need 1 cherry, I have 6. I could, in theory, make 6 sundaes using all the cherries up. That is assuming that I have more than enough of the other ingredients. When I look finally at my amount of chocolate syrup, I only have 100 milliliters. And since 50 milliliters is required to make 1 sundae, and having 100, I could only make 2 sundaes using all of the syrup. So in this case, my chocolate syrup would be my limiting reactant, because once I run out of the chocolate syrup, I can't make any more sundaes. And then I would have 4 scoops of the ice cream and 4 cherries that would be left over. Okay, so now let's look at the steps that would be involved in solving a limiting reactant problem. Now, I just want you to understand, as we begin this process, there are multiple ways that you can go about solving these limiting reactant problems. There is a separate video that I have created which goes over a few different methods for solving the limiting reactant problems. Today is just used to kind of help you get a basic overall understanding of what is taking place. So when we do this, same thing as we did before, we need to write a balanced equation for the reaction. And now the big difference here, you're going to have, instead of just one amount given, you're going to have 2 amounts or more that are given, one for each reactant, and you're going to solve for the same unit and substance. Whichever answer is the smaller amount, because that is going to be showing how much could be theoretically produced by consuming all of that particular reactant, the smaller amount of product will be your correct answer. And then to find out how much of the excess reactant is left over, we would simply start with that initial amount of the limiting reactant and solve for the excess reactants amount in that same unit. And then you could subtract that value from the initial amount of the excess reactant, and that'll tell you how much is left over. So we're going to now work on a couple of different example problems to help you guys kind of see the steps involved in this process. And the first example problem that we're going to do is what volume of hydrogen gas at STP is produced from the reaction of 50 grams of magnesium and 75 grams of hydrochloric acid. How much of the excess reagent is left over in grams? So the first thing we need to do is get our balanced chemical equation. So take a moment and balance that. You should hopefully see 1 Mg, 2 HCl's, 1 MgCl2, and 1 H2. So as we start off the problem, we're going to begin by looking at the 50.0 grams of magnesium. And since I have grams of magnesium, I'm going to use my periodic table. 1 mole of magnesium, 24.31 grams. That will now get my grams to cancel. I need to get the moles to cancel, so I'm going to take the moles of magnesium, which my coefficient is 1 in this case. And I have 1 for the coefficient of the H2 as well. So I'd have 1 mole of H2 over 1 mole of Mg. That will get the moles to cancel for magnesium. And now I need to get the moles of H2 to cancel. So I'm trying to solve for volume. So I can say 1 mole of H2 gas, 22.4 liters of H2 gas. And we can now solve. And when we plug those values in, we end up with 46.1 liters of H2 gas. So I'm now going to do the same thing, but this time start off with the 75 grams of the HCl. So I would have 75.0 grams of the HCl, 1 mole of the HCl, using your periodic table, 36.46 grams. That gets me out of grams into moles. So now I'm going to use my molar ratio. Notice again I have 2 moles this time for the HCl. So I have 2 moles of HCl on the bottom. That gets rid of the moles of HCl. And I have 1 mole of the H2. Now, it is vital that you guys solve for the same unit in the problem so that way we have that true apples to apples type of comparison. So if you notice, the last step for each of these different problems is identical. 1 mole of H2, 22.4 liters of H2. That way when we plug in and solve, we know whichever one is the smaller amount, that is going to show us the reactant that runs out first. So in this particular instance, when I plug my values in, I end up with 23.1 liters of H2 gas. I guess it would be 23.0 in this case. So my final answer would be the smaller of the two amounts, 23.0 liters. But we have a second part of the problem. So I have how much of the excess reagent is left over in grams. So what I want to do, and again, multiple ways you can go about solving these problems, but to solve for that excess, I'm going to take the limiting amount that we started with, the 75.0 grams in this case, because that is my limiting reactant for the HCl. So I'm going to take the 75.0 grams of the HCl, and I'm going to convert it into grams of magnesium. So I would have 1 mole of HCl being the equivalent of 36.46 grams of HCl. And then for every 2 moles of HCl, we had 1 mole of magnesium. And then finally, 1 mole of magnesium, 24.31 grams of magnesium. This way, again, my grams of HCl, my moles of HCl, moles of Mg all cancel, and I'm left with grams of the Mg. So when I plug those values in, 75 divided by 36.46 divided by 2 times 24.3, that gives us 24.99. So I have 25.0 for my grams of Mg that was consumed. And so now I can simply take my initial amount and subtract my used amount, and that'll tell me how much is left over. So I started initially with 50 grams. We used up 25.0 grams, so that would tell me that I would have 25.0 grams left over. Now that doesn't normally happen when it's a nice perfect half, but in this case it did. So the second application that we're going to look at is percent yield. So percent yield basically describes how much of the product was actually made in the lab versus how much should have been made in the lab. So you can think about the percent yield essentially telling us how effective or efficient we were at running a chemical reaction. Now, there are plenty of scenarios where the reaction will not work perfectly. You can have experimental errors, which would be spills or contaminations, which often means that the amount of product made in the lab does not match the ideal amount that could have been made. It could also represent a reaction that does not go to completion, which is what we call an equilibrium reaction. And in those types of reactions, even though we have a certain amount of each reactant still left in the reaction mixture, they still don't react completely together. And so you'd get a smaller amount of product than what you would expect. A couple of vocabulary terms here. We have the theoretical yield. which is the maximum amount of product that could be formed from a given amount of reactants. So you're doing this from the stoichiometry calculations. It doesn't have to be mass to mass. It could be just depending on whatever the problem is giving it to you as for the amount of product formed. So it could be liters, it could be molecules, it doesn't really matter. But it would be the maximum amount in theory that we could create of that product. And then we have the actual yield, which is the amount of product that we physically recover from a reaction carried out in the laboratory. And then from there, we have our equation for percent yield, which is simply taking the actual yield, what we produce in the lab, dividing it by the theoretical yield, what we should get maximum, and multiplying it by 100%. Now, for our work, you will never get a percent yield that is greater than 100%. We can't create more product out of thin air than what we actually started with. So it cannot violate the law of conservation of mass. Now, there are instances where we can have some experimental errors that will lead us to having a yield over 100%, but that would always be an error process that would be taking place. The last thing that I want to tell you guys right now is just a way for you to recognize what type of problem that you have. So for both the percent yield and the limiting reactant problems, you're going to be given two amounts in the question, but a very easy way to recognize it: your limiting reactant, both amounts are for reactants. When we're dealing with a percent yield problem, you'd have one reactant and one product amount that would be given. Okay, so just an easy way to kind of help you figure it out. If you see that you have a number for a reactant and for a product, you're going to be doing the percent yield. The product, that would be your actual yield, and then you have to convert the reactant amount into that product to get the theoretical yield. For the limiting reactants, you would have a starting amount for each of your reactants, and then you solve for whatever product you're looking for. So let's look at an example problem. When copper is heated with an excess of sulfur, copper 1 sulfide is formed. In a given experiment, 1.5 grams of copper was heated with excess sulfur to yield 1.76 grams of copper 1 sulfide. What is the theoretical yield and what is the percent yield? So again, the first thing we need to do is set up our balanced equation. So I have Cu plus S forming Cu2S. For my balanced chemical equation, I have 2Cu plus S forming Cu2S. So at this point, we now have an amount of one of our reactants. So again, I have 1.5 grams of copper. And you'll notice here that I'm given a second amount, but it's for copper 1 sulfide. So I have one amount that is a reactant, one amount that is a product. So that's going to tell me that I have a percent yield problem. Again, in this case, since it's asking you for the percent yield, it makes it pretty obvious, but in some cases it won't be quite so obviously worded that that's what it's looking for. So that's just an easy way for you to kind of figure out what you're doing. So as we look at this problem, to start off with, solving for the theoretical yield, that's just the stoichiometry. So I have a mass of copper, and I'm going to a mass of the copper 1 sulfide. So I'm going to start 1.50 for my grams of copper, and using my periodic table, 1 mole of copper, 63.55 grams. And now that gets rid of the grams of copper. I need to get rid of the moles of copper. So for every 2 moles of copper, we have 1 mole of the copper 2 sulfide. The moles of copper cancel, and I'm left with moles of copper 2 sulfide. And then finally, I need to convert 1 mole of the copper 2 sulfide into grams of the copper 2 sulfide. And if we do that, we end up with 159.17 grams. Okay, so my theoretical yield in this case will be equal to 1.88 grams of copper 1 sulfide. Okay, so that's part 1 for my answer. And then to solve for the percent yield, again, you'll notice that they tell us how much was actually created, which was the 1.76. So that is my actual yield. So again, actual yield divided by theoretical yield times 100%. So my actual yield is the 1.76 grams of the copper 2 sulfide, dividing that by the 1.88 grams of the copper 2 sulfide, and we would multiply that by 100%. So 1.76 divided by 1.88, that gives us 93.6%. Okay. Now, unfortunately, we can have problems where we have both limiting reactants and percent yields all wrapped up into one. So let's take a look at one of those types of problems to finish up for today. So for this combination problem, we're going to look at a fuel mixture used in the early days of rocketry, consisted of 2 liquids, hydrazine, N2H4, and dinitrogen tetroxide, N2O4, which ignite on contact to form nitrogen gas and water vapor. So we have 2 N2H4 as a liquid plus N2O4 as a liquid, forms 3 N2 as a gas and 4 H2O as a gas. So the first part, how many grams of nitrogen gas will form when 1.00 times 10 to the second grams of N2H4 and 2.00 times 10 to the second grams of N2O4 are mixed together. So hopefully you'll notice I'm given a starting amount of each of my 2 reactants, and I'm asked to solve for the nitrogen gas in terms of its grams. So I have 2 sets of reactant molecules, so I need to figure out which one of them is going to be the limiting reactant in part A. So to start off with, if I look at the N2O4, I have 200 grams of that, so 2.00 times 10 to the second grams of the N2O4. And we need to convert that into moles. So 1 mole of N2O4 should be 92.02 grams of the N2O4. And now my molar ratio, 1 mole of N2O4 will produce 3 moles of N2. And since we're going to grams of N2, 1 mole of N2, 28.02 grams. Again, just using my periodic table. So my grams of the N2O4 cancel, my moles of the N2O4 cancel, moles of N2 cancel, and I'm left with grams of N2. So as I plug in my values, 200 divided by 92.02 times 3 and times 28.02. That should give us 182.7 for my grams of N2. I do realize we only need 3 significant figures, but I want to wait to do my final rounding just in case the other amount is really close. So if I look at the N2H4, we started with 1.00 times 10 to the second grams of the N2H4, and in this case 1 mole of N2H4. If we use our periodic table, that would be 32.06 for the grams. And now my mole ratio, 2 moles of N2H4 produce 3 moles of N2. And finally, 1 mole of N2, 28.02 grams. So now let's plug that in and solve. So 100 divided by 32.06 times 3 divided by 2 times 28.02, and we end up with 131.1 for my grams of N2. So obviously 131.1, much smaller than the 182.7. So this is my limiting reactant here. So my final answer, rounded to 3 significant figures, will be 131 grams of N2. So that's my part A. So now, as my part B, it tells me that we had 112 grams that forms. So again, that represents the actual yield for the problem. And so to figure out the percent yield, I just calculated the theoretical yield in part A. So I have this as my theoretical yield. So to solve for the percent yield, I can take the 112 grams of N2 divided by the 131 grams of N2 and multiply by 100%. And if we plug those in, we end up with 85.5%. All right, well, that will conclude the stoichiometry videos. You will need to go and watch the methods for doing limiting reactant problems for our next class, and that will give you a way to kind of see which method you like to use to solve these problems. So have a good evening and work on your practice problems.